So next, let's look at a parameterization of a hyperbola. And that is the hyperbola x squared over a squared minus y squared over b squared is equal to 1. So notice that the point a times secant t, b times tangent t is on the hyperbola whenever cosine of t is not equal to 0, that is when these functions are defined. So let's replace x with a times secant t, and so x squared is a squared secant squared t over a squared minus, we'll replace y with b times the tangent of t, and so we have b squared tangent squared t over b squared, and that is all equal to 1. So we have secant squared t minus tangent squared t is equal to 1, or secant squared t is 1 plus tangent squared t, which is a trigonometric identity. And so either side, secant squared t is equal to secant squared t, and so that is correct. This point is on the hyperbola, and so a parameterization of the hyperbola is given by x is equal to a times the secant of t, and y is b times the tangent of t, where, as we will see, this equation gives us two branches of a hyperbola, and so to trace the branch on the right, we vary the parameter t from negative pi over 2 to pi over 2, and to trace the branch on the left, we vary the parameter t from pi over 2 to 3 pi over 2. So let's look at the parts of a hyperbola. Again, we'll use the variable k for eccentricity, and we'll set the eccentricity at 1.5. Then the parameter b is equal to a times the square root of the eccentricity squared minus 1. And now we can plot our hyperbola, x squared divided by a squared minus y squared divided by b squared is equal to 1. So we see right away that the hyperbola has two branches, and so we're going to have two foci. One focus occurs at the point a times the eccentricity, 0, and a second focus occurs at the point negative a times the eccentricity, 0. The hyperbola also has a center. It is the midpoint of the line segment joining the two foci, and so here that is the origin. A hyperbola also has two vertices. One vertex occurs at the point A0, and a second vertex occurs at the point negative A0. Now, a hyperbola also has two covertices, and those occur at the points 0b and 0 negative b. Now, notice that the co-vertices are not part of the hyperbola, but they can be used to construct a rectangle whose diagonals determine the asymptotes for the hyperbola. And so let's first consider the point of intersection of the horizontal line through the co-vertex V1 and the vertical line through the vertex V1. We'll call that point B1. And so that point will have coordinates AB. If we now look at the point of intersection of the horizontal line through the co-vertex U2 and the vertical line through the vertex V1, then we have a second point, and that one has coordinates A, negative B. So next we'll look at the point of intersection between the horizontal line through the co-vertex U2 and the vertical line through the vertex V2. That point of intersection has coordinates negative A, negative B. And finally, we'll look at the point of intersection of the horizontal line through the co-vertex U1 and the vertical line through the vertex V2. And that point of intersection will have the coordinates negative A, B. So we can now join these points to form a rectangle. Now, notice that the line that goes to the two vertices B1 and B3 will go through the center and the point B1. And so the slope of that line is B divided by A. And so one of the asymptotes is the line y equals B divided by A times X. And the line that goes through the vertices B2 and B4 will go through the center and the point B2. And so that line will have slope negative B divided by A. And so a second asymptote is the line y equals negative B divided by A times X. So again, the co-vertices are not part of the hyperbola, but they can be used to construct a rectangle. And the lines that go through the diagonals of that rectangle determine or are the asymptotes for the two branches of the hyperbola. So let's review the terms. A hyperbola has two foci, two vertices, and a center. The line segment connecting the two vertices is called the transverse axis. A hyperbola also has two co-vertices, and the line segment connecting the two co-vertices is called the conjugate axis. The co-vertices are useful because they help construct a rectangle, and the lines through the diagonals of that rectangle are the asymptotes of the hyperbola. So now that we have a standard equation for each of the three main conics, we want to be able to obtain the most generalized form of standard equation for these conics using transformations. So an active transformation changes the position of a figure or collection of points while leaving the coordinate system fixed. A passive transformation changes the coordinate system that describes the figure or collection of points. Now, in general, if T is an active transformation, then T inverse is the corresponding passive transformation. So, to apply a transformation to a figure or collection of points, we use the active transformation and to apply a transformation to an equation, f of xy is equal to 0, where an equation is a description of a curve in a given coordinate system. And so to apply a transformation to an equation, we use the passive transformation. So let's review rotation in the plane. The standard rotation matrix, rotation by theta radians counterclockwise, is the matrix cosine theta, negative sine theta as the first row, sine theta, cosine theta as the second row. Now we're going to take the transformation, or rather the transpose of this matrix, and the transpose of the matrix takes the first row and makes it the first column. and takes the second row and makes it the second column. So let's now multiply the R by R transpose. So we have cosine squared plus sine squared theta, cosine squared theta plus sine squared theta. Sine theta times cosine theta minus sine theta times cosine theta. Now for the second column, we have cosine theta times sine theta minus cosine theta times sine theta. And finally, we have sine squared theta plus cosine squared theta. So this is the atrigonometric identity. So this is 1, 0, 0, 1, and this is the identity matrix. So now let's multiply the transpose of R times R. So we have cosine squared theta plus sine squared theta. Negative sine theta times cosine theta plus sine theta times cosine theta. Now second column, negative cosine theta times sine theta plus cosine theta times sine theta. And finally, sine squared theta plus cosine squared theta. And again, this is the identity matrix. So since R times R transpose is the same as R transpose times R, which is the identity matrix, the transpose of R is the inverse of R. And so if we want the passive transformation corresponding to the rotation R, then we use the transpose, which is the inverse of R. So let's consider rotation by pi by 2 radians. Then that is the matrix cosine pi over 2, negative sine pi over 2, sine pi over 2, cosine pi over 2. And that is the matrix 0, negative 1, 1, 0. And so applying an active transformation to a point, xy, gives negative y x. That is, the new x-coordinate is the negative of the original y-coordinate, and the new y-coordinate is the original x-coordinate. So let's look at the passive transformation, our inverse, pi over 2. We simply take the transpose of the rotation matrix, and so we have 1, -1 as the first column, 1, 0 as the second column, and so if we apply that to a point, xy, then we have y -x. That is, the new x-coordinate is the original y-coordinate, and the new y-coordinate is the negative of the original x-coordinate.